Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled Hex, Octal, Bcd, Grays, and Ascii codes. Okay, so what I'm going to try to do today is a quick walkthrough of how to use binary numbers, ones and zeros, in different combinations to perform some pretty cool things you can do about packaging information together. First and foremost is hex. Hex is a super handy shorthand notation for binary. As you guys have already probably seen yourself do and me do in these lectures, it is really hard to rattle off a string of ones and zeros. Okay, what hex is, and all it is, it's packaging binary data in groups of 4, so it's readable. Okay, because I can say to you 0 0 0 1 0 1 1 0 0 0 0 1 1 1 1 0 0 0 1, and you're going to get lost after the first one. Okay, because the deal is I'm not breaking it up into readable data. If I broke it up in 4 chunks, in chunks of 4, it's easier to kind of put all those puzzle pieces together. What you do is you just have a shorthand notation for them, where each chunk of 4 is assigned a single sequential character. And the sequential characters that we use for the first 9, appropriately enough, the first 10, are appropriately enough are 0 through 9. So when you got 4 zeros, and this is, by the way, the decimal over here, and decimal, again, we have a problem here because once we get to 9, we have to use 2 sequential characters. Okay, so we don't want to use these 2-digit sequential characters. In hex, we're going to package them up this way: 0, quadruple 0, obviously means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The similarities end here. What's the next single-digit sequential character beyond 9? It's not 10. Okay, so you have to go to a different system, and the system that people used is A, B, C, D, E, and F. Okay, when I say to you C, 8, what I'm saying is 1 1 0 1 0 0 0. C 8 is a whole lot easier to understand than 1 1 0 0 1 0 0 0 0. I mean, I just messed up even saying that. What I'm saying is C8. Look at C. It's 1 1 0 0. Look at 8. 1 0 0 0. All it is binary shorthand. To package things into hex to make them readable, just divide it up into groups of 4. So let's say I have the 8-bit binary number like that. How am I going to divide this up into hex? Well, divide it up into 4-bit usable groups. There's 4. There's 4. Okay, what is 0 1 0 1 in hex? Right there. That's a 5. What is 1 1 0 1 in hex? Right there. That's a D. So I can say 5D. What I mean is 0 1 0 1 1 1 0 1. But 5D is certainly a lot easier to say and to write. Let's take this string and divide that up into 4-bit usable chunks and put it into hex. And you might be wondering, okay, where do I start? Okay, you always start from the LSB because there's 7 bits here. This, because that's the LSB and that's the MSB. I can always pad these things out. If I've really got 7 bits, what if I just put a 0 in the front of it? I can't put a 1 in front of it, but I can always pad out with leading zeros. What is our first set of hex chunks? 0 1 1 0. It's 6, followed by 1 1 0 6E. What if I asked you to, okay, you guys should be able to convert from binary to hex to binary pretty easily. Let's just go ahead and do an example. I want you to go ahead and say this is hex, binary, hex. Let's say 3FG4. Okay, now go ahead and convert those to binary. These are examples. Let's go ahead and do this string right here. Convert that to hex. So your answers for these should be, again, pause the recording if you need to go ahead and practice this. 3 is 0, 0, 1, 1. What's F? 1, 2, 3, 4 ones. G, 4. Uh-oh, there's no G. Okay, be aware inappropriate characters within there. Let's go ahead and let's do 6, 4 in hex. Okay, how am I going to tell you that that 6, 4 is different than 64? Okay, what I can do is I can say base 16, because that's what hexadecimal is. It's 16 positions, just like binary, 0 through 0 and 1, it's 2 positions. Additionally, you'll sometimes see people do this, H for hex. Okay, so I'm not confusing the number 64 decimal with 64 hexadecimal. So base 16. So 64 is 0, 1, 1, 0. 4 is 0, 1, 0, 0. That is converting 64 hexadecimal, or base 16, into binary. Let's go ahead the other way. 1, 0, 0, 0. That's an 8. 0, 1, 1, 0. That's a 6. And I can say H. 8, 6, H, hexadecimal. Finally, 1, 1, 0, 0. That's a C. 0, 1, 0, 0. That's a 4 in hexadecimal. How do I convert hexadecimal to decimal and vice versa? There are bunches of ways of doing it. Repeated division by 16, you can do all that. I don't want to give you guys useless stuff. There is just an easier way. Just do hex to binary to decimal. You know how to do that. That's easy. Okay, so these guys right here are the same numbers we did over here. We converted from 3F to binary, 3F hexadecimal to binary. How are we going to convert that to decimal? Just do the exact same thing we've been doing along here, is go ahead and add up 32 plus 16 plus 8 plus 4 plus 2 plus 1. What you should get should be 63. So 3F in hexadecimal is 63 in decimal. It's 0, 0, 1, 1, quadruple 1 in binary, and obviously that's hex. Okay, what's this guy? That's 100. Let's go the other way, decimal to hexadecimal. Let's say 40. Well, 40 has got 0, 0, 132, 1, 8, no 4s, no 2s, no 1s. Package it up, groups of 4. That's a 2, that's an 8, and 6, base 16. The number 28 base 16 is equal to 40 in decimal. And I know there's all these tricks about counting and hexadecimal, adding and multiplying. Don't worry about it. All we're doing is binary shorthand. Okay, so here's a particularly challenging example problems here. Is I've got example A in this row, B, and C. What I want you to do is take the number that's given to you and find and do the conversion to the other one. Okay, notice they're all the same numbers. They're all using the same symbols. 1, 0, 1, 0. This one is using it in hex. 1, 0, 1, 0, i.e. 1010 in decimal, and 1, 0, 1, 0 in binary. So go ahead and try to make those conversions, illustrating to you we're using the same symbols in different languages, and I'll tell you what language we're looking at here. Okay, so hex, we're going to convert it to binary. What's a 1 in binary? 0, 0, 0, 1. What's a 0? 1, 2, 3, 4 zeros. What's a 1? 1, 2, 3 zeros with a 1. 1, 2, 3, 4. That's the binary representation. Do you see what a pain that is? As opposed to saying 1, 0, 1, 0, base 16, or hexadecimal. Go ahead and see if you can work some of these things through by yourself, and you'll hopefully come up with these same answers right here, which I fill in this table. Okay, so for original hex value of 1010, you get the binary string, obviously 0, 0, 0, 1, quadruple 0, triple 0, 1, quadruple 0, which converts into a decimal 412 if we are, 4,112, we're using straight binary. Our 1010 converts to 0011, quadruple 1, 0010, which if we break it out into its 4 pieces for the hexadecimal, we get 3, and you might have had to have those padding double zeros there, 3F2. Finally, we were given 1010 in binary, which converts to 10 in decimal. And look up in our little formula there, excuse me, our little cheat sheet, 1010. That's A in base 16. So you should be able to adeptly transfer between hex to binary, binary to hex, hex to decimal, decimal to hexadecimal, binary to decimal, and decimal to binary. And to complicate matters, let's go on to octal. Octal, as hexadecimal implies, octal we're limited to 8 different sequential characters. I used to say in a previous incantation of this digital electronics lecture series, I used to say my octal lecture was as follows: no one uses octal. And I've since been proven wrong, okay, by our one of our PLC's instructors. People do use octal still, unfortunately. What is octal? It's 3-bit packages. All it is, it's representative of the time when there was 3-bit systems as opposed to a 4-bit system. And we've since expanded beyond that, but that is the easiest way for us to represent it. So a 3-bit representation, just look at our numbers up here. We are limited to the following subset of our truth table here, or possible combinations. We can represent 0 through 7 using 3 bits. And what we use is those same characters, 0 through 7. Once we get to 7, we count up to 10. Then we get up to 17, and then we go to 20. Okay, don't worry so much about the counting of these things. Worry about the conversion of these things. Okay, so now if I gave you this bit string here, it's the same bit string divided up into groups of 3, and assign it those characters 0 through 7. It's the same stuff, except we're looking at it with smaller chunks. So for the first 3, I got a 000. What's a 000? It's a 0. Next one, I got a 010. What's that? 2. What's the next one? I got a 000. 0 with another 000. 0 with 001. What's that? A 1. Finally, we got a 0. We're going to add padding 2 zeros, so 0. That is the octal representation of that same binary bit string. Does that make sense? All it is a different scheme of numbering, very common on some PLCs produced by Alan Bradley. Like I said previously, I didn't even really discuss octal until I was corrected by another instructor. It's helpful for you to know. Okay, see if you can go ahead and convert this bit string into octal, convert that bit string into octal. Go ahead and try that yourself. Let's go ahead and divide these up into groups of 3. So 010, 2, 110, 6. You maxed it out. Triple ones. So 7, 001. That's a 1 in octal. 1762. Base 8 is equivalent to 1010 in decimal. Finally, divide this guy up. 010. That's a 2. Add in some leading zeros there, so you're packaging it up in groups of 3. All these numbers mean the same thing. It just so happens that we're in different bases. What are the usable numbers? So we've talked about hexadecimal, we've talked about octal. Let's talk about BCD, binary coded decimal. As the name implies, it is concerned with only the decimal numbers 0 through 9. There exists none of this stuff here. Okay, so BCD is concerned with only these guys right here. All the rest of this stuff is invalid. And if you send any of those invalid codes to something like a 7-segment display, what I've talked about a 7-segment display here, A, B, C, D, E, F, G, with a 7-segment display, and we'll actually go into how these things work, I can display any of those decimal numbers 0 through 9. I have a hard time displaying the number 10 on a single-digit display. That's why those numbers are invalid. And if you try to send those invalid numbers, okay, try to show me the number 13 on a single 7-segment display. The thing's going to explode in your face. Actually, just kidding. It's just going to give you some weird values. What I'm saying is binary coded decimal, it just limits itself to the expression of decimal numbers using 0 through 9. How do we express, however, numbers with two 7-segment displays? For example, I want to display the number 23. Well, the answer is just send 2 to one of them and send 3 to the other. I can express the number 23 in several different ways. So number 23 in regular binary. There is a 16, there is no 8, there is a 4, there is a 2, there is a 1. Let's go ahead and package that up into appropriate values. Let's check our work. Okay, that's 23 in regular binary. But if I try to send 0001 to this guy, or 0111 to the other one, what am I actually sending? I'm sending the number 1. I'm sending the number 7 to that one. That's not 17. You know, that's going to light up like this. 17. That's not exactly the number that I want to display. I want to display 23. Like I said earlier, what you do is you just package the decimal numbers up into readable 4-bit chunks. What's the code for 2? Right there, 0010. What's the code for 3? 0011. Send this one to that one, send that one to this one. And by the way, there is a code converter, which we'll be talking about a little bit later. It's a BCD 7-segment display decoder. We'll talk about it. All I'm doing is just dividing it up into 4-bit chunks. What is the BCD representation of decimal 23? It's 2, 3. Same number, different bit strings. Straight binary, BCD. Same number. Let's say 48. Okay, what's the number in binary? What's the number in BCD? BCD should be super simple, and that's why I like BCD. 48 is 4, 0, 1, 0, 0, and 8, 1, 0, 0. That's the BCD representation of it. This is also called the 8421 code because that's 8421, and that's 8421, so on and so forth. It's got the weights of a 4-bit code. What's the binary representation of 48? So that's 32 plus 16, which is 48. Two totally different codes using ones and zeros to represent the same decimal number, 48. 96. Go ahead and see if you can do that one. Let's do 18. Binary and BCD. Okay, the binary representation should be extremely easy to you by now because you've been practicing this. And BCD should be even easier than that. 9, 6, 1, 8. Get it? Okay, we're rapidly drawing to a close here. We've already discussed hexadecimal, octal, and BCD, which leads us to grays and the Ascii codes. Before we go into grays, which is actually the description of these little pictures here that I've got described, one of my favorite topics is gray code. Pretty cool application of this. Let's just go over Ascii because that's kind of boring. All Ascii is, it's an 8-bit code for the alphanumeric characters. It's actually 7, but the 8th bit, the MSB, is always a 0. All those character combinations and all those invisible characters like spaces and whatever, and even all those weird punctuations, they're all assigned part of this 7-bit code. You know, for example, the letter P is assigned, let me write this down, 1, 0, 1, 1, 2, 3, 4 zeros. So that's the letter P, and I previously alluded to this. You press a key on your keyboard, obviously it's going to be encoded into the Ascii equivalent for P, which is 101 quadruple 0. What you do, let's go ahead and just use an example. How do you convert this to hexadecimal? Again, you got to pad that other to a 4-bit representation. That is 50. So sometimes you'll see the Ascii equivalents written in hex. Nothing too complicated about Ascii. Let's go into gray code. Okay, so gray code, like I said, it's one of the cooler applications of some binary codes. And what these things are is disk encoders. There's a difference between them, obviously, how they look. This one's in binary. This one's in Gray's code. Okay, Gray's code was invented, I think, in the 40s by this dude, Frank Gray. And he called it reflected binary. And what reflected binary is, or Gray's code, because as it eventually became known, it's a cool way of sequencing binary numbers such that only one bit changes at a time. Let me illustrate to you the problems or how it works here in binary. So when I count up from 0, I go to 1-bit changes. The LSB changes, dig it? And in a perfect world, when we count up to 2, A1 and A0 instantly, simultaneously change to 1 and respectively 0. They instantly and simultaneously change in a perfect world. They don't in reality because there are delays, and in those binary disk encoders, could you imagine, I'm going to go ahead and draw on this slip ring these brushes that are running along this disk encoder. And let's say there are positions of black and white on there, 1s and 0s. In a perfect world, brush A2, A1, A0 are perfectly aligned. But notice how, so they all simultaneously change. That's what I'm saying. Notice how A0 is ever so slightly ahead than A1 and A2. Okay, so and what I'm representing is kind of this very problematic. Let's do it in a timing diagram. A0, A1, A2. One would expect as we count up, so that's a 0 state, that's a 1 state. Now we're going to go to 2, because that is 0, 0, 0, 0, 0, 1. Then we are clearly at 0, 1, 0. What happens if this one changes ever so slightly sooner? The LSB changes ever so slightly sooner than A1. It's a glitch state. Again, one of those glitches. We are mistakenly in position 0 again. That's a problem with a binary encoder. It's clearly rotating from position 0 to position 1, and you would expect it to go to position 2, but briefly you think it's going backwards for some reason. I'm now in state 0. Oh no, wait, I'm in state 2. And now we go to, one would expect, state 3, so on and so forth, until we get to state 4, where this thing, the LSB, mistakenly again changes a little bit too early, and we're mistakenly reading ourselves in position 2 momentarily, and then finally it goes to 1, 0, 0, i.e. state 4. Okay, so this is a problem with binary encoders. What Frank Gray decided to do was called reflected binary. So reflected binary is a position where is an accepted code where only 1-bit position changes at a time. It's advantageous because you know that there is no possibility of those glitch states. I'm going to spare you the problems, and I'm just going to go ahead and write this down. Okay, so here's our all possible combinations in a binary sequence where we go from quadruple 0 to 1. Only one position has changed, so we're good there. Potential glitch state because that guy and that guy change. We're good here, only that guy's changed, so we're good there. What I'm illustrating is now we've got another glitch state because not only are these changing, that's changing simultaneously. That could be a potential glitch state there. So what the binary, excuse me, what the Gray's code is sequencing these binary numbers such that only one changes at a time. Well, it's called reflected binary because what it is, if you're counting in 2 bits, is 0, 0, 0, 1. Ordinarily, we'd go to 1, 0, but in Gray's code, you go to 1, 1. So only this one changes. And now we go to 1, 0. So then only that one changes. Only one changes at a time. To count in 3-bit Gray's code, this is why it's called reflected. Put 0s there, put 1s here, and perform a mirror image of this across there. 1, 0, 1, 1, 0, 1, 0, 0. Count in 4. And I'm not going to ask you to count in 3-bit and 4-bit Gray's code. I'm going to ask you to count in 2-bit Gray's code. Very essential for the K-maps, which we'll learn a little bit later. Again, reflect it, pad all these with 0s, pad all these with 1s, 8 1s, reflect it so it's 100, 101, 111, so on and so forth. That's what's called the reflected Gray's code. Brief clip on an application example of a Gray's encoder on a motor. Again, it's telling you what position it is. Because you're interested in 2-bit Gray's code, because it's essential for a later task, you count from 00 to 01 to 1110. Super, super critical in the K-map, which I'm alluding to right here. Gray's code. People have failed the final exams because they can't get this. It's absolutely essential to understand this. Gray's code, Gray's code, Gray's code in K-maps. Such that what we're creating is this matrix where any transition left and right or up or down is a change in 1 bit. Exactly like this encoder is trying to do right here. This about summates it for hexadecimal, octal, BCD, Grays, and the Ascii code. I'm asking that you guys be able to convert from binary to decimal, to hexadecimal, to octal, to BCD, back and forth and back, with your eyes closed, upside down, underwater. This concludes this portion of the lecture. We're going to go into some applications of these codes using decoders and displays.